This is IoT 204, Connected Robots, IoT in the Warehouse. I'm Paul Caponetti. I'm an IoT Solutions Engineer with Google.
Hi, I'm Christopher Cacioppo. I'm the CTO and one of the co-founders of 6 River Systems.
And I'm Joseph Hughes, Director of DevOps at 6 River Systems.
We'll be talking about collaborative robotics and how it helps companies meet the ever-changing needs of today's consumers. So, quick agenda. I'm going to take some time initially to try and frame some of the problems that warehouses are trying to solve today. I'll also go through some of the cloud solutions that help. I'll then hand over to Chris Cacioppo here for a double click on the business case for collaborative robotics and a little more information about 6 River Systems. And then Joe will finish up with all of the tech behind 6 River Systems and the products that they offer. So there is a dory for today's session, and I'm told if you go to the app and go to our session, IoT 204, you can see a link down below. Dory is an internal tool built at Google that's being made available at Next. You can go here to post your questions for us while we speak. You can also see the questions that others are posting. You can upvote and downvote those questions as you see fit. The idea is at the end of the presentation, we'll have a bit of a stack ranking of what the audience wants to hear from us. We're going to aim to end 6 minutes, 7 minutes early to try and get as many of these questions answered as possible. And afterward, we'll be able to answer questions offline. So, quick survey so I know who's in the audience today. How many people out there, by show of hands, are developers, architects, people that are building systems? We have quite a bit. That's great. There's definitely content for you. How many people are in the warehouse space working with warehouse management systems? Show of hands. Good. We got a bunch. How about robotics? Working with Ross? Great. There's a bunch of those too. How many people have ever bought a physical product on the internet? All right, good. Captive audience. So in all seriousness, this is the audience that we built the talk for. Hopefully you find some of this useful. So what are the needs of the warehouse today? And as an IoT developer that's been working on a lot of different connected products, working with a lot of different IoT cloud solutions, the first thing that strikes me is the sheer amount of data available. So there's products, there's product locations, there's LiDAR points, there's all sorts of things that without the technology you had, and now adding robots, you have things like batteries, robot statuses, many, many, many different types of data. And as a person that's managing a warehouse, I want to know that there's a way of obtaining this data. There's a way of reacting to it, formatting it. And Google Cloud has you covered. If you're able to connect your edge devices and your sensors to Cloud IoT Core, you can quickly, securely, and easily get that data to the cloud. From IoT Core, you get your data into PubSub. PubSub can act as a kind of central point in your cloud architecture. From there, you'd be able to trigger cloud functions to react to your data, or data flows, data proc, to be able to transform your data into an optimal format, and then ultimately sync it to BigQuery. And I say BigQuery, there's a lot of different data persistence mechanisms available on Data Cloud, but BigQuery, I believe, is uniquely well suited to the problems warehouses are faced with today. BigQuery is Google's serverless data warehouse in the cloud, and it's built to excel with analytics workloads. So let's say you have your data publishing to the cloud, you have it formatted, you have it synced to BigQuery. You're quickly faced with the next daunting task. There's so many things that you could potentially change in your warehouse to try and optimize your pick rates or find bottlenecks or just overall get your throughput up. You could potentially be spending man-months on a part of your system that, even if done perfectly, would only shave a small amount of time off your average pick rate, where there may be a bottleneck elsewhere that if you spent a couple man-hours, you would unlock a whole bunch more throughput. The quickest way to get to this insight is, since your data's in BigQuery, you can hook it up to Data Studio or many of the other business intelligence suites out there to visualize your data and understand where the time is being spent. armed with these visualizations, you'd know that spending man-months trying to make your user interface on your robot more effective for the picker might not be as impactful as maybe increasing the speed of your robot or your object avoidance or your slotting of your products, because move time dwarfs the amount of time that it takes to pick a product out of a box. So there's a certain level of insight you could get to with dashboards, but to potentially move beyond, you can try and employ machine learning. Machine learning might uncover different patterns in the data that might not be readily apparent with a dashboard or a visualization. It also may help in not only leading you to the opportunities for improvement, but be the improvement itself. You can potentially create models you can deploy on a robot and have that robot be more effective in its day-to-day job. One of the best things about Google Cloud and machine learning on Google Cloud is you don't need an army of data scientists or TensorFlow developers to be able to start to take advantage of it. Since your data's in BigQuery, you can use BigQuery AutoML to write a SQL statement that, say, returns your pick times and all of the different facets that might affect that pick time. And then with two extra lines of code, you can generate a TensorFlow model that forecasts that pick time when you change some of the other parameters around it. And just like that, you might know the effect of a change that you intend to make on your system. You can take it, same data in BigQuery and return robot failures and come up with a model that gives you predictive maintenance. You can use none of that data and use a pre-canned model that would give a robot the ability to see whether an obstacle in its way is human or not. And for those of you that aren't in the robotics space, this is valuable because a robot moving very fast in close proximity to a human would make that human very uncomfortable, very understandably so. But if a robot can't deduce whether or not an obstacle is human, it would have to slow down for every road cone, every piece of box, or anything in its way, and that could dramatically impact the pick rates. So let's say you have your data, it's in the cloud, it's in BigQuery, you have your visualizations, and you started to pick things that you want to change about your system to optimize it. Now you're faced with another problem, because to be able to get the data you need to validate those changes are in fact having a positive impact on your system could be costly. You can't change the size of your warehouse very easily or scale up your robot fleet for one day to 3, 4, 5x. It's pretty cost prohibitive to do things like that. So this is where Google Kubernetes Engine can help. You can spool up simulated robots and simulated warehouses and fuel BigQuery with the same types of data you would get if those robots were real. That then fuels the same dashboards that you used to pick what optimizations you wanted to take. So this is how you can quickly validate your change and iterate on to the next. Now, before I hand over to Chris, I wanted to quickly introduce 6 River Systems. 6 River was founded on the idea that the technological advantages that are seen in the large million-square-foot warehouses by the e-commerce giants should be available to all. So not only should these robotic systems scale up very well, they should be able to scale down. Traditionally, to get a fleet of robots in a 500,000 square foot warehouse, you're talking about 6 months to 12 months. You're talking about many, many years before the ROI pans out. These types of upfront costs don't work for the 50,000 square foot warehouse. So 6 River has a system that can be installed and up and running in weeks and fluctuate the size of your fleet for peak times and get ROI a lot quicker. What they're trying to do is, in effect, democratize robotics and level the playing field. With that, I'll hand it over to Chris.
Thank you, Paul. So why did we decide to use collaborative robotics to solve a warehouse problem? And at the end of the day, I want to give you a quick idea of the problem space, and then we'll talk about that. Up until about 10 years ago, distribution centers were places where manufacturers bought a lot of cases of product. They were then separated out and then shipped off to stores to then fill their stocks. So there was pretty much moving cases from place to place, which is reasonably easy to automate. They're nice, easy to touch and square, and it doesn't require a ton of labor. But in the last 10 years, things have changed. When you guys order things online, you never want a case of toothbrushes. You want a toothbrush and a toothpaste, maybe an iPad and some diapers, right? They're all different for everybody. And so it requires people breaking open cases, taking things apart, dealing with odd-shaped items. And so the warehouses look more like this. So there are people working on automatic hands and arms, and you've probably seen picking challenges, and they always pick off nice, clean pick faces. But it's clearly, for us, at least 5 or 10 years off before they have robotic arms and go in, take things apart, pull things together, gift wrap, all that stuff that requires labor. So there's a tremendous labor impact for the foreseeable future in this area. To make matters worse, when I was a kid, it was my birthday, and my mom would order stuff from the Sears catalog, and we'd mail it in, and it would take 6 to 8 weeks to show up, and I would have forgotten what it was, but I'm sure I was excited to get it anyway. Well, in the 90s and early 2000s, shipping times were about 2 weeks. So you order something online for early e-commerce, they show up in 2 weeks, everyone was happy, it was great. But today's day and age, people expect things, entry level is 2-day shipping, then it's like 1 day, and like it'd be nice if you showed up this afternoon. And so the pressure that puts on the fulfillment centers to get things out the door is tremendous. So like many things, as latency goes down, the efficiencies get worse, and so there's even more pressure on labor. These fulfillment centers and distribution centers are located in places where land is inexpensive, and before didn't need a lot of labor, but they've kind of sucked up all of the available labor. I was with a customer about 2 weeks ago, and they said, it's not so much that I care about the price of labor, though I'm sure they do, it's that I literally can't get people to reliably show up anymore. I can't get enough people to do. So what we've done is to solve this problem with Chuck. And Chuck, do you want to come over here? So Chuck is dressed up in his Google best. Chuck is a collaborative robotic robot. And the thing I want to point out here is this makes the associates' lives much easier, but everyone in our company is super excited about robots. And I think most people in this talk would think robots are pretty cool. Some cameras out there, so that's pretty cool. But people that are often associates working in warehouses, robots can be scary for a number of reasons. And so one of the things we did is, when I started this, I didn't want a little circle or rectangle or square in a warehouse that wasn't obvious what it was going to do. So I put on my industrial engineering hat and said, okay, we got a good designer, and said, I want this to be obvious. So this has clearly been modeled after a car. It's got headlights and taillights. It looks like a car, and when you look at it, no one here thinks it's going to go that way. It's going to go that way. And if it backs up, which it does very rarely, it's going to beep and look like a truck. So what we want to do is get people comfortable with the concept so that they're comfortable working it. If people are not comfortable working with your collaborative robotics, they're not going to use it, and nothing's going to work well. So we've had very good luck, and everyone loves using our robots. So the way a typical warehouse works for cart pick operations, an associate will walk over to an induct area with a big, heavy cart, and they'll put a whole bunch of boxes on it and get a whole bunch of paper tickets and walk over to their picking racks. It's going to look like a Costco or a back of an IKEA or a Sam's Club, except much more dense. They're then going to walk up and down a whole bunch of aisles, fulfilling the orders with these paper tickets and finding everything where they remember, and then they're going to bring it over to a takeoff area, or possibly multiple ones, and then do that big loop. Okay? At Six River, we decided what's most important that the associates can do is, that much better than anyone else, is the grasping of the hand. So we want to try to alleviate as much of the other stuff they're doing as possible. And these aren't small places. As we talked about, these are 50K to 500K or more warehouses. They're a tremendous amount of movement. So what our system does is there's a person who sits in an induct area on top, and they put work on the robot. And then the robot takes off. Okay? The robot will then meet someone in the picking area. They will then walk with them through the area, showing them pictures taken from place to place in the best method possible. And then when they're done, that robot will take off and deliver it to multiple places potentially, and another robot will be waiting for them. So we'll keep them localized in doing what they do best in the picking aisles. What we can do is improve pick rates 2 to 3x over traditional cart pick. Okay? And we do this by a number of ways. We reduce the long walks so that people have to walk across giant warehouses. We very effectively pick orders that go together in a nice, clean way so they walk as little as possible. We pick them optimally from place to place. And we also have very clean UIs, which lets them get the data fast, so they can pick faster, they can lower error rates, and they can reduce training time from weeks to hours. And this has been hugely positive for our customers. The next thing about Chuck that's very interesting is it's a disruptive technology. So there's a number of technologies out there that allow cart picking, that enhance cart picking or replace cart picking. So, but most of these operations have 3 to 5 years ROI and are bolted in the floor. And I don't know about anyone in this audience, but I have no idea where my company's going to be in 3 to 5 years. Like, technology changes so fast, it is a tremendous investment to do. To make matters worse, there's generally in this industry, there's a huge seasonal change. So right around holiday season, most of our customers see a 3 to 7x change in their operation, right? Tremendous changes. So not only do you have to predict potentially 5 or more years in the future, but you also have to scale up so that your operation is running pretty much at peak time, and then 80% of your time it's significantly underutilized. So what we allow to happen is we have a 2 to 1 year ROI for our products. They can, instead of being installed, most automation is 6 months to a year of installation time. We get up and running in 1 to 2 weeks, okay? It also allows you to scale your operation. If your operation is getting more and more, going up and up, you just buy more robots. We just deliver them, they work as is. If your operation's scaling down, well, if you have another DC or another fulfillment center, just move the robots. If you have seasonality, just instead of building a system from 6 River that works for your peak for the entire year, just build for your average for the year, and we'll lease you more robots for your peak time. So we allow a tremendous amount of flexibility that is just not possible anywhere else in the industry. So from the first day I sat down on my dining room table with my 2 other co-founders, to the day we had a small fleet of collaborative robots picking live orders, I believe it was toys, in a customer warehouse, was 9 months, which is, looking back on it, felt much longer, but it's an amazing feat. And I don't think this is possible 10 years ago, even with the best group of people you could have. And the reason is, I think there's 3 key technologies over the last 10 years that have made a tremendous change. One is the ubiquitous computing power. So we've invested in NVIDIA's Jetson's TX2 platform. And so that gives a tremendous amount of processing power at very low energy consumption at a reasonable price point. And so we've done a lot of work with them. But it's not just that. It's all the sensors and all the things that allow robotics to work have come down tremendously in price. It wasn't that long ago that the spinning lidars you see on top of the Google cars, they cost like 50 grand. But now we can have ones in the robots that cost less than 1,000. So there's a huge change in technology that's enabling things that just weren't possible before. The second one is open source, which I'm sure everyone here uses. It's gotten better and better over the last 10 years. I want to call out ROS. ROS is a robot operating system for your non-roboticists. It allows you to bootstrap robots really fast, so you can focus on the things that your business cares about and not focusing on the plumbing and infrastructure. So we could very quickly get a robot up and working, and then pile more stuff on top of it to optimize it for our environments. And last but not least is the ubiquitous cloud platforms. And we've embraced Google Cloud from day one. This allows you to scale the operations, leverage your engineers we have, do a lot of testing stuff we have, a lot of security things. It just allowed us to go so much faster than we would have otherwise. So given the audience, I think we'll spend the rest of the time talking about the Google Cloud. So one thing that's very important to me personally is data-driven decisions. Pretty much this entire conference is about data, right? And so collecting data, and everyone knows data is good, but how do you use data? How do you make it effective for you? So let me go through some of the ways we use it. And we have a lot of data, both from the logistics side and also from the robot side. If you haven't worked with robots, robots generate a tremendous amount of data and make lots of decisions, and it's very hard to churn through all the data otherwise. The first thing we do is operational intelligence. We have a ton of data on all of our customers' operation, and we can tell them how much work they're doing, how much time they have left, the rates they do things, a whole bunch of stuff. We can say which of their associates are performing better and worse. But even more than that, instead of saying, Chris is underperforming, I can say, Chris seems to be doing pretty well. He's just really slow at scanning. Maybe he doesn't know how that section works. And so an associate can come to me and help coach me through something that I'm weak at, as opposed to just dealing with it or deciding they should get some other employee, if that's even possible. The next thing is visualizing data. This is one of my favorite things. So this up here is a picture of our robots go through the warehouse all the time. They report back wireless signal strength constantly, so every second or so. And so this is a map of the wireless signal strengths at various parts of the warehouse. So people do wireless surveys, and they're sort of ad hoc and occasionally happen. But we are constantly real time showing a wireless survey of the warehouse. So you can tell in this warehouse, there's a big area in the center that's probably pretty weak, and if the customer cares, they should probably update that. But I think what's more important is how we use it for our internal engineering personally. So when you're starting to build a robot, you get a robot, and what do you have to do first? You have to make it move. Check, it moves. And then we don't just want it to move. We want it to move from A to B. So we want it to move over there. Excellent. Check, we got to move A to B. And then you want it not to hit things. All right, check. And you go through this whole list of things, whether it's robots or any product you guys do, until you get an MVP and it's in front of the customer. At that point, that's great. We get some feedback and we work on the most important things next. How do we choose the most important things? In most operations, it's done in one of three ways. One, the manager or whoever's in charge decides. Two, the loudest engineer decides. Or three, if you're doing things probably correctly, you have a consensus of engineers that decide together. But the problem is, even in the latter case, where you have a consensus, it doesn't mean you're working on the right thing or most important thing first. You just all agree. You can all agree on the wrong thing. So this is a graph up here about the time that the associates are spending on our product, which is important of labor management and labor savings. So the big blue box here is movement. It says the largest amount of time, about 44%, is spent on the robot moving from points A to points B with the associate in tow. There are other things down here, such as scanning, right? And so one of our engineers may have a great idea. We can just remove scanning entirely. And that sounds like a great idea. We can just skip that step and be awesome. Let's work on that. And someone else has an idea that says, we can reduce movement 20%. That doesn't sound as good. But if you look at the numbers, it's way better to spend time reducing movement by 20% than it is removing a stage, even though it doesn't intuitively feel like just removing something isn't just a better idea. So I'm going to give an example of that. This is another customer warehouse, and instead of plotting Wi-Fi signal strength, we're plotting average movement speed of the robots. So you can see red is slower, green is faster. So if you look at some of this and analyze a little bit, at the end of aisles, things are slowing down. It makes sense. There's cross traffic, there's blind turns. You got to be a little more careful around that. But there's slow areas in the middle of the aisles, which doesn't make a lot of sense, right? Robots should be humming along there. It should be fine. So we can do two things here, and we do both of them. One is we can push back on our customers and say, hey, you guys should clean this up. The robots move faster, and your rates will go up. But really, it's better if, like, why are we slowing down? Like, so, because everybody wants the robots to move faster. So I think, obviously, the next thing we do is just make the robots top speed faster. Or is it? So some of our engineers took some of our robots and put it in a test track. And instead of just reporting the maximum speed in robots, they report the internal choices of robots. And essentially, crash course in robotics here, we have a bunch of different tasks that determine how fast a robot can go. And the slowest one wins, because we believe in safety and everything else. So whatever chooses the slowest, that's the one that we go at. So if you look up here, red says I'm near an obstacle. Yellow says go top speed. So if you look up there and we increase our top speed, really wouldn't have had a giant impact on our robot right now. Because mostly we're having around objects and we're slowing ourselves down because we're being extra careful. So the engineers took this data and attacking that problem instead of trying to make the robot respond faster to go faster, and analyze that problem. And after a couple of weeks, they did the test track again. And this is what they got. You'll notice instead of being like 85% red, it's now like 40% red. And there's a lot of that yellow, which is the top speed. The robot's just cruising along at top speed. So there was a huge impact of diving into this problem, and it resulted in about a 15% movement speed increase. And now that the engineers can look at this and say, okay, should we keep pushing on that problem? Should we look at the teal over here, which is a pathing issue? Should we think about raising top speed? But it allows a data-driven decision when obviously, everyone says, we should just make the robots move faster, and that was actually the wrong decision. So that's my part of the talk. I'm going to hand it off to Joe, who makes all the magic happen here.
Thanks, Chris. So you just got hired at the next IoT robotics company. And you wake up the next day, you're feeling good, but then you think to yourself, I need a robot infrastructure. Lucky for you, you're here at Google Cloud next, and we're going to help you to understand how we've used Google Cloud to address some of the most challenging aspects of this problem. The first and most obvious problem is you have all this data. You have hundreds of robots in the field. You have robots that are in your test environments and your customer environments. You have to get all this data, and you have to make some sort of sense out of it. So we're going to talk about this slide for the next 30 minutes. All right, you guys didn't run away. We're not going to do that. But I think here there's an important thing that I want to point out about this architecture. We don't just use Cloud IoT Core for everything. We also use Google Storage for a couple things. And the reason we do that is that there's some data that is really important to have in real time. But there's other data that we may need later that is really dense. And Chris talked a little bit about that data. That's your LiDAR scans, your point clouds, the roboticist. If you're not a roboticist, that's really kind of what the robot is seeing and logging all of that. And we need to put that into Google Storage because those files are big, they're dense, and then we need to run it and break it down. So we make heavy use of PubSub and cloud functions to massage that data, get it into the format that we can consume. Some of that data comes all the way back through to a web page where people can consume it. Some of that data goes to BigQuery, and that's what drives some of those interesting graphs that Chris showed you before. What we're going to be doing next is using that data in BigQuery, as Paul alluded to earlier, to drive some machine learning models so we can get better and think more about the data that we're collecting. But this infrastructure for us, this design has survived the test of time and scaled with us with no engineering intervention at all. So one of the things that you want from this data is real-time location. You may think to yourself, well, that seems important, but I'm going to explain to you why it's very important. If you're managing a 1 million square foot warehouse and you can't have line of sight to everything, so you need a bird's eye view of what's going on. You have 25 trucks in the field, you might have 50 employees in the field, and you really need that real-time feedback. So most obviously, you just need to know where trucks are. If you can only see 10 trucks at a time, you need to know where the other 10 are and make sure they're doing the things that you expect that they should be doing in your warehouse. You also want to see if Chuck's in trouble. You'll see 2 trucks here blinking red. If a warehouse manager was to click on one of those, they could see that there's an obstacle in Chuck's way, or that there's some other unexpected event, maybe some sort of maintenance that needs to be done to Chuck. In any case, it really calls out very clearly that there's a problem that needs to be resolved. They can get on a radio, talk to someone and ask them what the problem is, or they can make the decision to walk over. But if you're constantly walking around a 1 million square foot warehouse looking for problems, most likely you're not going to be able to find them. Lastly, you want to understand the operation. So if you see trucks queuing up in a weird way, or you see that trucks and your operators are not in the right part of the warehouse for where they need to be at that point in the day, then you can correct that and make sure that you still hit your rates. And that means that everyone in the audience gets their shoes on time, or their toothbrushes on time, or whatever you might be ordering off the internet. The next big thing that you want from all this data is real-time monitoring. Our customers run 24/7. The internet's up 24/7. People are ordering 24/7, and you expect your stuff in 2 days. So we have a tech support team that also runs 24/7. And when something comes in, they need to really quickly respond. Now, for our cloud software that's running in the cloud, Stackdriver was a clear choice. Out of the box, it gave us alerting, it gave us all the monitoring that we could possibly want, and we didn't have to invest any engineering time into instrumenting. It just came with the platform. We use Google Core IoT to feed data into InfluxDB for a time series database, and then also drive the dashboards like you see behind me. This gives us our CPU metrics, our memory metrics, and our temperature metrics. Some of these warehouses get up to over 100 degrees, so the temperature of their CPU becomes super important. If your fan fails and your CPU is overheating, you're going to have a very unhappy robot, and eventually you'll have a very unhappy customer. But this really all drives preventative maintenance. If we can take a truck out of service before it fails and clogs up the works, then we can save our customer time. they may be running a degraded system for a little bit, but hopefully we can pull the truck out of service, replace a part from a spare part kit, and get truck back in and doing its job. Lastly, we touched on this a little earlier, but enabling technical support is super important. They're really the front line of defense, and they need tools to help the customer resolve their problems quickly and not interrupt engineering. If engineers are spending all their time solving customer issues in the field, then they're not going to be able to build the next great feature and make Chuck better. And we're constantly doing the experiments like Chris showed you earlier to make Chuck faster and to continually raise our customers' rates through just software and better engineering practices. So this is the second type of data that we were talking about in that architecture slide. This is data that's not really valuable in real time from every single Chuck because it's very dense and it gives you the whole picture of what Chuck sees in the world. But you may want this data because you want to replay Chuck travel. You get something from the field and say, hey, Chuck is moving strangely around this shelf, or Chuck can't see this particular thing on the ground, or something of that nature. And that comes to our engineering team, and we need to be able to see that. And so we have two options. We can get on a plane, we can fly over to the warehouse, go take a look at Chuck, and say, oh, well, I guess I can hook in and take a look at the sensors. Or maybe it's not even doing that anymore by the time you get there, but planes are expensive and engineering time is also expensive. Or you can replay this truck travel from Google Cloud, you pull that down, and you can replay in real time. So what you're seeing on the right of this is you can actually see Chuck seeing other Chucks. On the left, you can see shelves. That's what's called a point cloud. You can see it's made up of a lot of points. From this, our engineers can deduce a lot of interesting things. There's your test environment, which you have in your warehouse, where you do all your tests and you try really hard to make Chuck move the right way all the time. Inevitably, though, you get out into the field and there's things you didn't expect. These, we call them movement issues. They're caused by some interesting things. Some customers shine their floors, or they have skylights, and that feeds back into the sensors and makes this point cloud much different than it does look at our headquarters and our test track. Help improve efficiency. Chris kind of alluded to this earlier. But if there's a specific place in the warehouse where the trucks just always move slow, sometimes what we can do is clearly just see that the LiDAR or the camera is seeing something that it shouldn't. And with a little bit of adjustment by the customer or a little bit of adjustment in the map that we use to navigate, we can alleviate those problems. So, you have all your data. But now you have 100, 1,000, 1,000,000 robots in the field, and you need to upgrade them at some point. So how do you do that? Traditional software management, Ansible, SaltStack, Puppet, they're great tools for managing servers. You have an always great internet connection, and you can kind of rely on that internet connection to make things good for you. The great white whale of Chuck is reliable Wi-Fi. Warehouses just don't have reliable Wi-Fi. There's a lot of racks, there's a lot of interference, and so what we end up with is half applied states. So almost worse than an upgrade just failing is a half upgrade. An upgrade that looks like it went good, but it didn't go all the way. And we battled a lot of these problems early on. So we said to ourselves, there has to be a better way. We have to be able to reduce the complexity of these things. We have to be able to minimize the amount of data that's being pulled down and do it more deterministically. So we shoehorned everything into Docker. Docker containers are pretty great at solving this problem. If you have a container, it either downloads or it doesn't. If you need to roll back, you roll back to a different container. You have a very good view of the world of where your software is updating. And so if you need to update 1,000 of these things, all you need is a good internet connection to download a single file versus what you would have to do in the other situation, which is a bit of a back and forth between a lot of different services. We really leverage Google Cloud's platform to make this possible. And don't get scared, it's another architecture slide, but we're going to go for it quickly. Google has a lot of great tools for building containers. Cloud Build scales with our developers. As they need to make containers and we're rushing to finish releases, then we can have 20 developers doing 20 different builds, and Google Cloud Build just scales up We push all those to the container registry. And then we have our custom solution to this problem. But really, Google has a great toolkit with Kubernetes Engine that you can run software that just consumes a lot of this stuff. And finally, this software allows us to push things out through IoT Core. IoT Core can't just collect data, but it can actually manage the configuration of the robots. So essentially, the message goes out to 1, 1,000, 1,000,000 robots saying, we need you to download this container from container registry. And then they go into action. So I'm going to show you how that works. Here's an actual upgrade. So this is sped up a little bit, but these containers download. The robot gets the command, gives us the signal that it downloaded, and then we can apply that upgrade. And so you'll see we do 3 at a time here. They download and they apply. And so we're taking 3 chucks out of service. We're downloading a container. That container gets applied. They go back into service. But we know exactly if something didn't work, if it did work. And the nice thing is going from build X to build Y is just as easy as going from build Y back to build X. Because I think all of us know that sometimes software upgrades don't go well. So almost as important as your upgrade path is your downgrade path. But with Docker, Kubernetes to drive this software, and IoT Core, we can really manage this problem very well. So we have all the data, we have thousands of robots, and now our customer comes and says to us, hey, we think we need to rearrange our entire warehouse. We have 100 chucks, and we think that this design might work better. And you're like, okay, well, so we're back into kind of a problem here. So we can either fly out to the warehouse, bring another 100 chucks, get another warehouse, set it up the way they want, test, and make sure that it works, or we have to do something else. And I think we all kind of realize we pretty much just have to do something else. So going back to our Docker adventure here, we were really pleased when we got to this point when we said, okay, we already have everything in Docker, so all we really need to do is change a few things in this container, and we'll actually have a Docker container that can be run in a simulated world. So we have the robot operating system running completely inside of the Docker container. All we do is simulate the sensor data. And so what's really powerful about this is that the sensor data coming in is going through the same pipeline that it would go through in the real world. So as we make adjustments, we can be very confident that those adjustments are going to behave the way that we expect them to in the real world. And that really just gives us that extra bit here where things, when we go to deploy them, behave the way that we want. So why would we want to test with hundreds of robots? The warehouse layout change is one thing, but another thing is algorithm changes. You know, we have a lot of logic and algorithms, as Chris alluded to earlier, that batch orders and to try to gain more efficiencies in the warehouse. And so when we change those algorithms, it's not really great for us to test them out on a customer, because you can imagine what a customer is going to call us and say. They're going to call us and say, hey, Joe, that software upgrade you gave me, now my rates just fell by 50%. And that's not a really great conversation to have. And that's not what we want to do for our customers. And so with this sort of infrastructure, we can prove algorithm changes before we deploy them. And we can confidently tell a customer, when you take this release, you're going to get X percent of improvement. Your pickers will be this much more efficient. Your warehouse will be able to get this many orders out the door, and be very confident that that's an accurate estimate. And lastly, and I think which is kind of an interesting way to use this system, is that we have cloud systems as well. And we can do synthetic load testing of those cloud systems and throw, foobar data at it, or we can run real simulated robots against that system and do load tests for warehouses that are even impractical to build in the physical world. So we can really put our other software in the cloud through the paces using a very large deployment of simulated chucks. So scaling with Kubernetes Engine is super easy. Auto-scaling works great. And that is really important for this problem. You don't want to have to call up a DevOps engineer and say, hey, I need a cluster with 100 simulated chucks, you just want to tell your software, I need 100 simulated chucks, and then minutes later, you have 100 simulated chucks. Stack driver monitoring is built in. And so you can see your simulated chucks and see trends in their CPU usage, their memory usage, and see all of that and feed it into BigQuery, as Paul alluded to earlier, and make sure that your dashboards perform the way that they should, and that you're seeing the algorithm improvements that you should. You can scale up and down quickly. Scaling up is super quick. Scaling down is also super quick because this is an expensive resource. And you don't want to be spending money with a simulation cluster that someone forgot to shut down for like a weekend, and your Google Cloud bill all of a sudden is a little bit higher than you expected. So here's a real simulation. This is a pretend warehouse in the cloud with pretend robots running around doing robot things. They're picking orders, they're inducting orders. They even go to charge. They even have simulated batteries. So because charging can actually take out of the efficiency of the system. So we simulate all of that, and we can put all of the things I talked about into this. And so this is a very, very flexible system. Another thing that happens is that when you start simulating things, if you spawn 20 robots in the corner of a warehouse, they kind of form a mosh pit, and they don't really do very well. And so these are some of the fun things that you start to discover when you build a simulation platform is like, oh, wait a second. They all can't just spawn in one place. They need to actually spawn at random points, and we need to kind of figure out how we scale this up and down. But yeah, that's a fun little video of a robot mosh pit if you ever wanted to see one. So the last thing we need to talk about is integrating with your customers. You didn't just build this robotic IoT platform for yourself. You built it because you wanted to bring it to the world, and you want people to use it, and companies to use it. And so you have to kind of discover who your customers are, discover what kind of technology they have, and you have to integrate with it. So in warehouse management systems are the systems that handle all the orders, handle all the inventory. They kind of determine like what that day's picking is going to be, and they give us our work. And so we have to integrate with them. Our customers have older systems. They're in the logistics business. They're not in the IT or the tech business. And so when they find a solution that works for them, they stay with that solution. And we don't want to go into our customers and say, well, we wish we could work with you, but you have to update all of your IT systems to adhere to REST standards and to our APIs. We have to do something different. So we adapt our REST APIs to our customers' technology. They use socket communication with fixed width messages. They use SOAP. They use SFTP. I mean, they use everything. And so that means we have to build everything, and we have to adapt our APIs to everything. And so that's a big challenge. But luckily, when you're using Google Cloud Platform, you have a lot of tools at your fingertips to help you with that challenge. We reach for cloud functions for the simplest of integrations. And Kubernetes also makes it super quick with things like Knative and other tools that are coming to the Kubernetes platform, where we can build these little microservices that their only purpose in life is to translate our API messages so that our customers can understand them. There's a lot of challenges still, but with these tools, without these tools, we wouldn't be able to do what we do today at the pace and at the scale we do it today. Google Kubernetes Engine on-prem is the next great thing that Six River Systems is really looking at. And some of our customers have such tight regulation. You can think government and those type of things where they just don't have the option to have anything outside of their four walls. And so with these type of deployments, we're really excited to experiment and to use Google Kubernetes on-prem to solve these problems. So these regulation concerns are definitely one part of it. Another part is to bring the latency-sensitive things that need to happen to the edge, and the edge being the customer's own infrastructure. And so if we have to validate something every single time we scan it, and we can't afford the trip up to our cloud, back to their data center, back to Chuck, then a system like this makes things a lot easier for the customer and for us to get that integration done and to really have a great customer experience. From our point of view, it's so great that we can have the same deployment tooling that manages all of our normal cloud deployments, manage these on-prem deployments as well. And so that can reduce our overhead for DevOps tooling and to keep the interface that we use for our software engineers and for our tech support engineers the same.